Hello and welcome. Today I would like to talk about a basic principle of trigonometry known as Pythagoras' theorem, which relates to right-angled triangles. I'm sure many of you have heard about this theorem, and for those of you who haven't, perhaps from school, I hope this video would be a good introduction to the topic. This theorem is fundamental to trigonometry, which is a world of its own, but builds upon Pythagoras' theorem to form many of its other laws. And you will be continuously using Pythagoras' theorem throughout trigonometry to solve many of its problems also. In this video, we will look at this topic from its ground principle. Let's start with a short introduction into the background of this theorem. A widely used theorem in antiquity, today the theorem is known after the Greek philosopher Pythagoras, who was also a mathematician. The ancients, like the Egyptians, used this theorem extensively, especially in construction projects like the pyramids. The Pythagorean theorem concerns a natural property of right-angled triangles, whereby the fulfillment of the theorem implies the correctness of the right-angled triangle. So what does that mean, the correctness of a right-angled triangle? You should know that a right-angled triangle is named such because of the 90-degree angle it forms between its two sides. But how do you draw an exact right-angled triangle without the necessary tools that we may have today to do so? In fact, how do you form those tools in the first place in order for you to determine 90 degrees exactly? Pythagoras' theorem is a mathematical formula that, if established for the sides of the triangle, will automatically mean that a 90-degree angle is formed between its two sides. Hence, verticality can be exactly determined. Utilizing a ruler of some sort that upholds the Pythagorean theorem, walls or other construction elements could be determined to be exactly vertical, hence ensuring correct and safe construction. We can be sure that without this naturally occurring principle, it would have been very difficult throughout time to construct buildings perfectly erect. Even so, up till today, the use of Pythagoras' theorem is so vast it extends beyond the subject of construction into astronomy, mathematics, and science in general, such that it forms an integral part of the subject of trigonometry. And so that is where we begin today. So now let's look at the basic components of a right-angled triangle. Notice that we use this symbol as a convention to indicate right angle. It is basically a vertical line on a horizontal line with a square to indicate 90 degrees. A right-angled triangle has three sides with two sides forming a 90-degree angle between them. The side opposite to the 90-degree angle is called the hypotenuse. Now let's look at a very unique construction of a right-angled triangle which may even have led to the discovery of Pythagoras' theorem in antiquity, one which is based upon the arithmetic progression of 3, 4 and 5. Let's take a string of 12 inches in length. Now mind you, it may be in meters or any other unit length of measurement, it does not matter. But for this example, let's say inches. Now let's partition this string at 3 inches, 4 inches, and the remainder would then be 5 inches. Notice that we have here an arithmetic progression formed from 12 inches. Also, a side note, for those of you who aren't familiar with what an arithmetic progression is, it is basically a sequence of values with a constant increment between each value. So in this case, between 3, 4 and 5, the constant increment is 1. So 3 increased by 1 becomes 4, and 4 increased by 1 to become 5. Let's now fold this string onto itself such that it forms a triangle. We find that in doing so, the sides of 3 inches and 4 inches form exactly 90 degrees. This is a consequence of nature, that this construction forms this condition. We can then say that the triangle with sides of 3, 4 and 5 units in arithmetic progression will invariably form a right-angled triangle. Incidentally enough, if we noticed, the length of a regular ruler that we usually use is also 12 inches long. I cannot say with proof that the two are linked, though it is an interesting point to note. Also, we know that all measurement methods are usually inherited from ancient construction methods which were built upon to the modern day conventions we use today. So perhaps it is why the standard ruler has such a conventional length. But regardless of whether or not that is, let's return to our topic of the day. There is something very special about right-angled triangles in that their sides interrelate to one another. If we were to take a unit square, meaning a square of 1 unit length sides, and stack a series of these at each side of a right-angled triangle, a unique pattern will begin to emerge. Let's begin with the side of 3 units. Stacking such squares to form a larger square would give 9 squares in total. In other words, squaring 3 gives 9. Repeating this step with the other sides, we find that for the side of 4 units, squared gives us a total of 16 squares. And with the hypotenuse of 5 units, squaring this gives us a total of 25 squares. Now observing these 3 squared values, we find that the sum of the squares of the sides of the triangle give the sum of the squares on the hypotenuse. In other words, 9 squares added to 16 squares gives 25 squares. Rewriting this, we recognize that 3 square plus 4 square equals 5 square. This is Pythagoras' theorem. A more generalized depiction of the theorem would be a square plus b square equals c square. A, B, and C being the sides forming a right-angled triangle, with C being the hypotenuse of the triangle. So let's look at some example questions on Pythagoras' theorem. We have here a triangle with sides 5, 12, and 13. We wish to determine if this is a right-angled triangle. If the combination of 5, 12, and 13 fulfills the condition a square plus b square equals c square, whereby a equals 5 and b equals 12 and c equals 13, then we know that the triangle formed by the sides measuring 5, 12, and 13 units must be right-angled. So let's investigate. If a is 5 and b is 12, then 5 squared plus 12 squared would equal 169. Suppose we take this value to be c squared. We know that 169 is 13 squared. So c squared equals 13 squared, and therefore c equals 13. Hence, Pythagoras' theorem is in fact fulfilled and the triangle is indeed proven to be right-angled. A second example problem. Suppose we want to build a right-angled triangle with sides 3.5 units and 1.5 units. We wish to determine the hypotenuse C such that the triangle formed will be right-angled. This can be done by making C fulfill Pythagoras' theorem, whereby a squared plus b squared should equal c squared. So a in our case is 3.5 units and b is 1.5 units, and we are to determine the value of c. So a squared plus b squared equals 3.5 squared plus 1.5 squared. This is 14.5. Now we want this to be c squared. So the square root of 14.5 would be c. This is 3.81 units, approximated to 2 decimal places, which suffices for our example here. Therefore, we can say that a right-angled triangle can be formed with the triple of 3.5 units, 1.5 units, and 3.81 units. So to sum up, we know that Pythagoras' theorem is named after the Greek philosopher Pythagoras of Samos, who was also a mathematician. It is a natural property of right-angled triangles and is used extensively throughout time for construction, astronomy, mathematics, and science in general, wherever verticality or a 90-degree angle needs to be determined accurately. Pythagoras' theorem states that considering the sides of a triangle, the sum of the squares of the two sides adjacent to the 90-degree angled corner equals the square of the hypotenuse. In other words, a squared plus b squared equals c squared. Lastly, we observed a unique right-angled triangle made up of the triple 3, 4, and 5. It is unique in that it forms a right-angled triangle in arithmetic progression. And so we've completed our topic today on Pythagoras' theorem. I hope you enjoyed this lesson and we wish to see you again in the next session. Thank you and till then.